Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to start week 11, which is centroids. Now, there's kind of good and bad news for centroids. Centroids are very, very easy. As you'll see, there's kind of a single formula for centroids, and that's all you'll need to remember. But even that formula is on your formula sheet, so you don't even really have to remember centroids. So the hardest part about centroids, as you'll see, is just there can be integration. Now, there's two scenarios you'll see with centroids, and one of them is a continuous body, and that's basically when you see kind of a calculus curve. It looks more like a math problem than an engineering problem, which is not the best. But the second example is when we see what we call a composite body. So a body that is it looks kind of complex, but it's actually just made up of simple shapes, and that'll be our next example, 11.2. So this week there'll only be two examples because that's all you need to know. So that's kind of the nice part about centroids. Very, very straightforward questions, very, very simple. There's only two scenarios. But then again, they kind of suck because they may involve some integration. And I know myself personally, I'm not good at integration. I'm very, very bad at integration. But kind of the nice part for you guys is this is an engineering course. This isn't a math course. So the hardest part about the integration for you guys should only be finding our integral. Because after we found our integral and find the boundaries and everything like that, we can just throw it in our calculator. So it's going to be my hint to you guys for the final. Please have a calculator that can do integration. Now, if you guys, let's say, finish the final early, well, we all know that's just a dream. No one will ever do that. But in case you do finish the final early, you guys can try the integration if you want, something like that. But realistically, all we want in this course is for you guys to get to the end and be able to have the integral, and then you can just throw it into your calculators. And there's going to be some tricks with that because we might give you an integral curve that has some constant parameters which may not be defined. But if that's the case, you guys should know that we can take the constants out of the integral, stuff like that. So we're going to cover kind of all the tricks for the integral. Now, in relation to the final exam, this is going to be very important because the fourth question, so kind of the last question of the final exam, a lot of people have been asking me lately, what's the final? It's always going to be kind of the same thing. The first question is going to be trusses. Second question is going to be those bending and shear moment diagrams. So those first two are very, very straightforward. You know what a truss looks like. You guys know what a beam looks like for bending and shear moment diagrams. It's one of those things that I always say bending and shear moment diagrams, but that's horribly incorrect. It's shear and bending moment diagrams. You guys have to start correcting me because that's going to sound super silly. But those are straightforward. You guys kind of know what to expect. And the third question, however, friction, it could be absolutely anything. And as you guys will know, I didn't do a lot of friction examples because it's hard to find good friction examples. So as you guys will see, I may not have done a lot of friction examples for week 10, but I'm going to do, let's say, an extra one or maybe an extra two, depending on how much you guys want it, for final exam questions. So I'm going to search friction questions from the final exam because those are what more likely to expect. Friction questions, sometimes they're just absolutely crazy, and there's no sense covering them because you'll never see them in a final. But the fourth question, which is kind of what we're covering today, it's going to be a bit of a mixture. So as before, week 7 was trusses, that's a final exam. Week 9, bending moment diagrams, that was a question. But now week 11, centroids, it's going to be kind of half of a final exam question. So the fourth question on the final exam is kind of a mixture. It's going to be half centroids, which is what we're going to learn today and then in the next video, and then half moment of inertia. A moment of inertia, though, the reason why they're the same question is because they're actually very, very closely related, very closely related. And if you guys can understand these formulas for centroids, the moment of inertia formulas are actually very, very similar. And if you guys can understand this, then moment of inertia is going to be kind of a piece of cake. It's kind of the exact same process, and you find them. And moment of inertia will have the same two scenarios. That I have a continuous body where you'll have to integrate, but personally, I've never really seen that on a final exam. And then you have a composite body, so a body made up of simple shapes, and those are very common on an exam. So kind of what I've seen in the past, half the exam will be centroids, half will be moment of inertia. What I've also seen is the centroid will typically probably be integration, while the moment of inertia will be a composite body, because they want to make sure that you know both. But the integration for a moment of inertia, although possible, and you guys can do it very easily, as you guys will see, it's a little bit more complex. So they usually like to save the integration for the centroids and then the composite body for the moment of inertia. But I'll show you all 4 scenarios so you guys will be super happy. And by 4 scenarios, I mean the composite and the continuous body for centroids, and then the composite and continuous bodies for moment of inertia. So there's going to be 4 examples total. And then, of course, probably next week we're going to get into the final exam questions, and I'll probably cover a couple of those for the moment of inertia and centroid. So you guys will have lots to study from. This will be pretty straightforward, but just remember, this will be on the test. And the reason why I say this is because back when I was in first year, it was the night before the final. Yours is at 2 o'clock, but ours was at 9. And I had a guy come to me at 1 in the morning, so 8 hours before the final, with a textbook, and he says, "Do you think moment of inertia will be on the exam?" Well, of course. It's been on every exam for the past 20 years. It's not going to change now. You can expect this on the final exam. Same with centroids. Moment of inertia, centroids are very closely related, so please make sure you know this. It will be on the exam. All right, so I think I've talked long enough. Let's jump into centroids specifically for a continuous body. Alrighty, so looking at this example, as you guys will see, there's no text, but all we want to do is find the centroid of this shape. And the shape is defined by y equals h over a squared times x squared. So we're given a function, and this is how you know you're going to have to use 1 or 2 centroid formulas. So before we get into that, let's just discuss the 2 centroid formulas. So there's going to be 2 possible formulas you guys are going to see on your formula sheet. The first is going to be this. And I'm just going to do the one for x, but the one for y is essentially the exact same. So if you understand the one for x, you'll understand the one for y. So it's x bar, and that bar means the centroid, is equal to the summation of ai, I guess in this case. So ai times x squiggle I, all divided by the summation of ai. And so the 2 things that you guys are going to want to know from this formula is this ai. Well, this is simple. This is just the area of a shape. So you guys know how to find area. And then this x squiggle, or oops, I did x bar. It's x squiggle. And I hopefully that people from other sections don't laugh at me. I know my section really got sick and tired of hearing me say squiggle. I don't know why. It doesn't sound that silly to me, but I guess you guys will think it's funny. So the x squiggle is the distance, and this is going to take a while to write. So it's the distance from the axis to the centroid. To the centroid. And now this part's going to be kind of important. Centroid of the shape, of the simple shape. Simple shape. So this formula right here, and I'm going to put this in red, this is for a composite body. So this is when your body is made up of a bunch of simple shapes. So this right here, composite body. You don't want to use this one for a question like this. It will not work. So this is for composite body. And again, we're going to talk about this a lot in the next video, so don't worry about this too much. But as you guys can see, the area, well, we know how to find the area of simple shapes. Because remember, a composite body will always be simple shapes. Triangles, squares, rectangles, stuff like that. So we can find the area of those. And we also know the centroids of those simple shapes. Like for a square, we know that the centroid is going to be right in the middle. So it'll be easy to find the distance from the axis all the way to the middle of that simple shape. But again, we're going to cover this in the next scenario. So this is case 1. So I'm just going to put a 1 here. And that is for composite body. So this will be, I don't know, put brackets, next example. So again, not too bad. We'll get to that later. So the second one, and this is the one we're going to want to pay attention to, is we're going to use this formula right here. X bar, so the same thing, the x coordinate of the centroid is going to be equal to the integral of x squiggle times dA divided by the integral of dA. So this is pretty much the exact same formula. The only thing that you guys have to kind of realize is x squiggle is the same as xi, And dA, well, that's the same as the area. And the only reason why we're doing dA is because we're taking the integral of it. So we're taking the integral over the whole shape so that dA will turn into just area once we integrate it. So it's the exact same thing. But the reason why this scares everybody is because of the integral. Anytime I put an integral in front of something, you guys are thinking, oh my gosh, this is math 100. This is not engineering. This is going to suck. And you guys are right. This does really suck because integrals suck. I've kind of gotten better, and I use the word kind of extremely loosely in this case because I'm still not the best at integrating, but integrals suck and they scare everybody. But again, this is an engineering course, so if we can figure out the integral, then we can just throw it into our calculators. Now, this is going to be kind of a special case, if you will, because this is all constants. So in this case, we can't really throw it into our calculators. Usually on the exam, you can throw it into your calculators. But I chose this example very specifically because we can go through and see how to actually integrate. So if you are stuck in a situation and you have to integrate, well, I'll show you guys how. And these integrals are always very, very, very simple. So let's forget about the integral for a second, and let's just see. So we can find x bar if we know two things, and that is dA. Oops. So we need to know what dA is, and we also need to know what x squiggle is. And that's it. So although it looks very scary, realistically, all we have to do is find two parameters, and if we find those two parameters, we're good to go. We just throw them into there, and we go into our calculator and integrate it. So that's the hardest part, finding two parameters. And as you guys will see, it's actually not very, very difficult as long as you're using the right methodology. So real quick, I'm also going to put this formula right here is for a continuous body. So this is when they give you a curve or something like this. And I probably spelled continuous wrong. I'm not 100% sure. I'm not an English major, so who knows. So this is for a continuous body. And for those of you who are wondering, that is this example. So if we look at this body, and actually we'll scroll up real quick. So if we look at this body, it's not composed of simple shapes. It's just one single curve, and it wants us to find the centroid of that shaded region. And that shaded region is very nice because it's continuous throughout the domain. So now we have to go down and say, okay, we know that our formula is going to be this x bar is equal to the integral of x squiggle dA divided by the integral of dA. So we have to find out what is dA, what is x bar. And by the time this video is up, you guys will already know kind of the procedure. I'm not sure how the other professors exactly do it, but it relies upon finding what we call a slice. And this slice is going to either be horizontal, so I'm going to draw it in purple real quick. So we're either going to take a horizontal slice of this area, or, and I mean or because both are correct, we can take a vertical slice of this area. So something like this. And depending on which way you take the slice, you guys can find those parameters dA and x bar. So that's the whole purpose of the slice, is to find dA and x squiggle, not x bar. We'll find x bar in the end, but we're looking for x squiggle right now. So now the question becomes, okay, do we take a horizontal slice or do we take a vertical slice? And the answer is it actually doesn't really matter. And for this example, I've actually done the integration for both. So I'm going to show you both, and this video might get a little lengthy because of this, but I'm going to show you both, and you guys can kind of decide which one you guys like better, because you guys will see the integrals, you guys will see what you have to do for both. But in my opinion, in this specific case, I think a horizontal slice might work better. And the only reason why I say this, and it's because of this scenario, is because of this right here. And where's my highlighter? It's because of this little space between where the curve starts and the x-axis. Normally you want to try and avoid that, and I'll show you guys why. So if we had a different curve, so I'm going to go to the side here, and let's say that, oops, I'm still on the highlighter. If we had an x and y axis kind of the same way, but our curve was like this, well, then I would probably want to take a vertical slice, because there's a distance here. Oops, I'm switching my pen. Because there's a distance between the y-axis and the curve. Usually you don't want to take a slice that would involve that distance. So if we look in scenario 1, our actual problem, we have that distance between our vertical slice and the axis. So that's kind of telling me I probably shouldn't go that way. If we were to take a horizontal slice in the second scenario, so if I were to go a horizontal slice like this, as you guys see, I have that distance between the y-axis and the curve. So that says I should probably, in the second scenario, take a vertical slice. And again, it doesn't really matter because both will give you the exact same answer. It's more dependent on how you guys want to do the integration. And I'll show you guys what exactly happens in the integration when we have that little jump there. So it's going to be kind of not a fun time, but I'll show you guys right now. So in this scenario, I'm going to put in red this one. I would, and this again, this is just me, I would go horizontal slice. Horizontal slice. In the second scenario, I would go vertical slice. And this is just me. I'll show you guys why specifically I do that. But again, it's completely up to you. It's whatever you guys are comfortable with. And I'm going to show you guys both methods. So for the first one, I'm going to show you guys what I consider the more easier of the two, and this is a horizontal slice. Horizontal slice. So what I'm going to do is I'm just going to copy this picture real quick, and I'm going to bring it down there so I can show you guys exactly what I'm going to do for the slice. How do I paste? This should work. Oh, perfect. So I'm going to amplify this a lot too so you guys can see exactly. Excuse the pixelation. I know it's going to look terrible. And I'm going to erase all the other stuff I did on it. Actually, I guess I should keep the horizontal slice because that's exactly what I'm doing. So this purple part right here, this is going to be my slice. And it doesn't matter where along the curve you put this slice because we're going to keep it all extremely parametric. But I'm just going to, let's see, I can't do it. So I'm going to redraw the slice. So the slice will start, and it's basically just taking a nice rectangle. So that's kind of the key here. We're taking a rectangle of the curve. So it's the exact same as integration. We're looking at a little fiber of this curve. And what we're going to do, because remember, our end goal right now is to say dA is equal to something, and our x squiggle is equal to something. So that's our goal right now. Our whole goal is to find out, okay, what is dA, what is x squiggle? And we're going to find those through the slice. So this dA, and this right here, I'm going to put right here, and I should probably do this in red. So the reason why we take the slice, because dA is equal to the area of the slice. So we're going to have to find the area of that slice. But if we look at the slice, it's just a rectangle. So we know that we just need the base times the height. So we're going to check what those are. And x squiggle is the distance from the axis to the centroid of the slice. So a lot of words right there, but you guys can remember this, you're good to go. So now let's go up to the slice, and we're going to try and figure out the parameters of the slice. So what we're going to do first is kind of go, okay, well, we need to find the area of that slice. So let's start to label some of the parameters. Now let's do this in green. So the thickness of the slice, this will be your easiest one. This one right here, we're taking a little fiber along the y-axis. So this thickness right here is going to be dy. And it'll always be like that. If we're taking a horizontal slice, that little thickness will always be dy because we're taking a little element, which we say is dy, along that y-axis. If I were to do a vertical slice real quick, so something like this, well, in this case, we're taking a little slice along the x-axis. So this right here would be dx. So there's one thing to know right there. But since we're taking a horizontal slice, it'll always be that thickness dy. So we already have one of the two parameters. The next one we're going to have to know is what is, oops. Let me get rid of the eraser real quick. Go back to the pen. So the next one is how long is this slice? So one of the things that you guys are going to have to remember is this slice can be anywhere. So we're not just looking at this specific point. We're looking at anywhere along the curve. So what is this distance? Well, let's say I know that this y value is equal to 2. We can find out this distance right here using this formula up here. We can rearrange this formula and we can go, okay, x right here is going to be equal to, and we can just rearrange the formula to say it's equal to a over h to the 1/2 and then y to the 1/2. So that's just rearranging the formula. So if we know y, we can figure out x at that point right there. If we know that the distance right here is equal to 3, or the y value is equal to 3, we can find this distance right here using the exact same formula. X is going to be equal to a divided by h to the 1/2 times y to the 1/2. So if we're going up to this distance right here, and this distance is equal to just y, because it can be anywhere along the slice, we know that this distance right here is going to be equal to x, and we know that x is going to be equal to a over h to the 1/2 times y to the 1/2. So now we know that distance. We can say it's either x, or we can substitute it to be equal to a divided by h to the 1/2, y to the 1/2. So that right there, we have our dA. So we come down here, and I'm just going to write dA. And we already know that this is equal to the area of the slice, so it's equal to the base, which is going to be x, and then times the thickness, which is going to be, or the height, I guess, which is going to be dy. But as you guys can see, this is already a problem, because this dy here, this is going to be how we integrate, where we're going to integrate with respect to y. But our equation right now has an x value in it. And this x value is not good because we cannot, at least the spoiler alert, I guess, you guys will see this later. Right now, we can't integrate x with respect to y. We want to integrate y with respect to y. So this is when we use our formula that we just did up here, where we substitute x in terms of y, so this one right here. Because from this one right here, what we can say is we can substitute that x for a function of y. So this right here is going to be equal to a divided by h to the 1/2. Oops. I'm going to make this a little bit nicer. H to the 1/2, y to the 1/2 dy. So now we got basically a constant times y and then a dy. So our only parameter in this equation now is y. And we're integrating with respect to dy, so it's perfect. Everything is really good in this case so far. So now we found one of the two. We found out what our dA is. But now we got to find out what x squiggle is. So for moment of inertia, oops, I always put x bar, but it's not x bar. X bar is our actual final answer. We're looking for x squiggle. So remember, looking at what we defined down here, our x squiggle is going to be the distance from the axis to the centroid of the slice. So if we look at the slice right now, it's centroid. Well, we know the centroid of a rectangle is right in the center. So we know that the centroid right here is going to be right here. That's the centroid. So our x squiggle right here, and I'll put this right here, it's going to be the distance from the axis, which is right there, to the centroid. So this right here is going to be our x squiggle. And if we look at this, that's just half of the length of the slice. So it's going to be equal to x over 2, because we're going halfway along that slice. So if we come down here, our x squiggle, that's going to be x divided by 2. Oops, maybe I should switch back to the regular color, or else it's going to look silly. It's going to be equal to x divided by 2. But again, we know in our formula, we can't do x, because everything is going to be in terms of y. So what we're going to have to do is substitute that in. So we're going to get 1/2. So that's just the x over 2. And then we're going to multiply that by a divided by h to the 1/2, y to the 1/2 times dy. Or sorry, no dy, because that's the dA. So I'm just going to put right here so you guys can see. This right here, this is equal to x. X right there. So now what we have is we have our dA and we have our x squiggle all in terms of y, and we're integrating with respect to y. So at this point, this is when you just throw everything into your calculator and you're good to go. So if I go down here and I write our formula again, and I'll write this in black, so we know that our x bar is going to be equal to the integral of x squiggle times dA divided by the integral of dA. Well, now we can just substitute what we know as dA and what we know as x squiggle into the formula. So it's actually equal to something very, very, very nice. So we come down here and we say, okay, well, we know that x bar is going to be equal to the integral. So the integral doesn't change of x squiggle. But now we know that x squiggle is going to be equal to 1/2 of a, or times a, divided by h to the 1/2, y to the 1/2. So this right here, that's just our x squiggle. And now we're going to have to put our dA in, which we know is equal to a divided by h to the 1/2 times y to the 1/2. And then all this is going to be a dy at the end. So now we're integrating with respect to y. So in the bottom, so this is just the top. And now the bottom, we have the integral of dA. So the integral, and we know that dA is equal to a to the a divided by h to the 1/2, y to the 1/2 times dy. So now this is really, really nice. We have an integral. We have a bunch of constants, and that's fine because we can, as we learned, we're just going to take those out. So who cares? And then from there, we can just substitute it into our calculator. But now we're going to see one problem that we have is when we go into our calculator, it's going to say, okay, great. You have y, you have a bunch of constants, you got your dy, everything's good. But now you're going to have to define the integral. So as you guys know, when we integrate something, we have to integrate it over a boundary. We have to integrate from which point to which point. That's kind of the whole thing that we're going to have to find. So we're going to come up here, and we're going to say, okay, am I integrating from, basically you got two options. So we got 0 on the axis, we got h up here, and we got a over here. So we have to ask ourselves, are we going to be integrating over the x-axis? So are we going to be integrating like that? Or are we going to be integrating over the y-axis? And it's actually very, very easy to tell because remember, integration is just taking a bunch of little rectangles over the axis and summing them up. And if we look at this right here, we see our rectangle is actually going along the y-axis because if we were to integrate this, we'd have a bunch of rectangles along the y-axis. But that's too complex for me. I don't want to get anything crazy. I want to keep this nice and simple. So the way I remember is if I have, and I come down to my equation, if I have a dy, so I'm integrating with respect to y, I'm going to write this down here in red. So if I have a dy, what this means is I'm integrating over the y-axis. So therefore, my bounds in this case, if I'm integrating over the y-axis, I'm going from 0 to, and I look at my y-axis up here, I'm going from 0 to h. So what this means is I'm integrating from 0 to h in this case. So if we come up to my integral again, I'm going to just copy it. Actually, it'll probably be easier if I just try this. I'm learning new tricks on the iPad. It only took me till the end of the semester, but better late than never, I guess. So if I come here, and this is my integral, I can now define these integrals. So I'm just going to erase the highlighting, like that. And now I can say that the integrals here are now from 0 to h. And then this one also the same, 0 to h. And if we're being nice in the final, this won't be from 0 to h. This will be from, let's say, 0 to 4. Like, these will be actual numbers, or else it'll get a little too silly. All right, but that's basically it. So now we come down here, and we're going to say, okay, well, I have an integral at the top, integral at the bottom. And if I can't use my calculator, unfortunately, I'm going to have to solve all this. So what I like to do in this case is I'm just going to go back, and I'm going to say x bar is going to be equal to one answer divided by the second answer. So what I like to do is I'm going to evaluate the top integral, and then I'm going to evaluate the bottom integral. Now, if you guys are using your calculators, you guys can do this all in one step. But even if you're using your calculators, I still recommend solving the two integrals separately. And the reason why is when we're finding centroids, we're only finding the x-coordinate right now. And later on, we're going to have to find the y-coordinate. And what's nice is this bottom piece of the integral down here, this second integral, we're going to use this exact integral in finding the y-coordinate. So if we have this on hand, when we're finding the y-coordinate, things will actually be a lot easier because we already have one of the integrals ready. But for now, I'm just going to go one integral divided by the second integral. So what I'm going to do is I'm going to go 1, which is equal to the top integral. So this is going to be equal to the integral from 0 to h. And then I'm just going to substitute all the values in. So we got 1/2 times a over h to the 1/2 times y to the 1/2. Now we're multiplying this by a divided by h to the 1/2 times y to the 1/2. And all this is going to be times dy. So before you start throwing these into your calculator, the best thing that you guys always want to do is just simplify things. So the first thing I'm going to do is, okay, I'm going to equal, and I see that I got a 1/2 here. So this 1/2, well, that's just a constant value. So remember, constants can come out. So I'm going to be equal to the equal to 1/2. So this is going to come out of the integral. And the integral is still going to be from 0 to h. That will never change. And we look at this and say, okay, well, I got an a. So I'm going to highlight this in a different color. I got a up top on one side. I got a on the other side. Well, a times a is going to be equal to a squared. And then at the bottom, I got an h to the 1/2 times h to the 1/2. So remember, when you're multiplying those exponents, you end up just adding them together. So you got 1/2 plus 1/2. Well, this is going to be equal to 1. So we're going to have a squared divided by h. And then finally, I'm going to change the colors again. I'm going to have y to the 1/2 times y to the 1/2. So again, we're going to add 1/2 to 1/2 to give us 1. So this is going to be equal to y and then times dy. So now our integral started off looking real crappy, but now it's starting to look a lot nicer. And now we can go down and simplify it further, because if we go, okay, if things are constant, we can pull them out of the integral. And a squared and h, well, those are going to be constants. So let's pull those out. So we're going to have a squared divided by 2h. Then we're going to have the integral from 0 to h. And the only thing we have left in this integral is just going to be y times dy. So the integral of y, well, that's actually very, very simple to solve. A lot of you guys will say, oh, that's very, very easy. We can do this very, very easily. So this is going to be equal to a squared divided by 2h. And now we're going to evaluate our integral. So remember, when we're integrating something, we're going to increase the exponent by 1. And whatever our exponent is in the end, we're going to divide everything by that number. So right now, we know we're going to have a y. And the exponent on the y right now was 1, y to the 1. So we're going to increase that by 1. So y to the 1 is going to change into y to the 2, so y squared. And then we're going to have to divide everything by the new exponent. So the new exponent is 2, so we're going to have to take everything and divide it by 2, just like that. And we're going to have to evaluate this integral from 0 to h. So this is one of those cases that y to the 0, well, that's just, 0 squared divided by 2, that's just going to be 0. So what this is actually going to be equal to is a squared divided by 2h, and then we're going to multiply this by h squared, so we're substituting h in for y, so h squared divided by 2, and I guess if you guys want to show the full integral, you're going to go minus 0 squared divided by 2, which is just going to be equal to 0. So now we can just put those two together. So if we look at this, well, we're going to have a squared divided by 2h, and we're going to multiply that by h squared divided by 2. Well, we can start to see some things cancel. So the h at the bottom, I'm just going to go to red to show some canceling. We know this is h squared is going to cancel with the h at the bottom. So it's just going to be h now on top. And the 2 multiplied by 2 is going to be equal to 4. So we know all of this right here is going to be equal to a squared multiplied by h divided by 4. So that's our first one right there. So not bad at all. Nice and nice and easy, if you will. So I'm going to highlight this. And actually, what I'm going to put real quick is this is equal to 1. So now later on when we come back and we're referencing 1, we already know the, oops, I got to switch to the right thing, highlighter, not pen. So now we already know what 1 is equal to. Highlight this nicely. Perfect. So now we found 1. But remember, our integral is, or our centroid is equal to 1 divided by 2. So now we got to find out, okay, what is 2? So we're going to come down here and we're going to say, okay, 2 we know is going to be equal to the integral dA, which we already defined. So if we look up here, it's going to be equal to the integral from 0 to h. We come up here, a squared, or actually I think it's just a. We look up, yeah, it's just a divided by h to the 1/2. So a divided by h to the 1/2, y to the 1/2 times dA, or not dA, dy. So that's just coming from what I have up there, where I have my integral 2. So we come down to here and we realize, okay, it's not as nice. We can't multiply everything together to get rid of the 1/2s, but we can still take out the constants. So we all know this is going to be equal to the integral, but we're going to take out all the constants. So a and h, those are constants. We can go a divided by h to the 1/2 multiplied by the integral from 0 to h, and then y to the 1/2 times dy. Okay, so that's not too bad. I personally, and I think you guys may feel the same, I'm not a big fan of integrating exponents that aren't whole numbers. It gets a little bit weird, but the way I like to do it is this. So I'm going to go, this is equal to a divided by h to the 1/2 times the integral of 0 to h. And what I'm going to do is I'm just going to make this into a number, not a fraction. 0.5 times dy. And the reason why is all those same rules apply. When we integrate something, we're going to increase the exponent by 1 and then divide by the new exponent. So we come down here, this is going to be equal to a divided by h to the 1/2. So when we integrate this, we're going to have y, and we're going to increase the 0.5 by 1. So this is going to be equal to 1.5, and we're going to divide by that new exponent. And in this case, our new exponent is going to be the 1/2. So what we're going to do is we're going to come down here and we're going to go 1/2, like this. I'm going to put brackets around this, and this is our new integral, and we're going from 0 to h. And again, when we sub 0 into this, it's just going to be equal to 0. So it's one of those things that you don't really have to do it 100%. So we come down here, we're going to go, this is equal to a divided by h to the 1/2. And then our integral now is just going to change from h to the 3 over 2. So this is when I'm going to convert back. 1/2 is just 3 over 2. And we're dividing all this by 3 over 2. Because again, 1/2 is just 3 over 2. So then we can do kind of our simplification, make things a little bit nicer, stuff like that. So we come down here, say, okay, all this is going to be equal to the 3 over 2. Well, if I put the 2 up top, it's going to be 2/3. And that just comes from the bottom there. H to the 3 over 2 divided by h to the 1/2. Remember, when we're dividing exponents, we just subtract them. So what we're doing is we're taking 1.5 and we're minusing 1/2. So what we're going to have is h, and then the a, well, that just stays there. So that's going to be equal to 2/3 of ha, ha, or a to the h. It all works the same. So what I'm going to do is I'm just going to highlight this so we can use it later. 2 is equal to 2/3 of a times h. And I'm just going to highlight this, because remember, this second one, the integral of dA, we're actually going to use later in our calculation for y bar, or the other one, the other centroid. So from here, we can say that x bar is going to be equal to 1 divided by 2. And now we know 1, and we also know 2. So we're going to come up here. 1 is equal to, what I like to do, and this is kind of cheap, but I just put it like this, 1/4 times a squared h. And I'll show you guys why I put it like that up top instead of trying to rearrange things. And at the bottom, we got 2/3 of AH. So now I'm going to take my nice red pen and start canceling stuff out. Well, we got H at the top, H at the bottom. We got A squared and then an A at the bottom. So we're going to take away the squared and take away the A at the bottom. And now this is what I do. And it's going to sound really, really funny, but, or not funny, it's just going to make me sound stupid. What I do in my calculator now is I just go 1/4 up top, divided by 2/3, and then I change it into a fraction. So I don't try to calculate it myself, even though it's definitely doable, and I'm just extremely lazy. But what you guys will find out is that our x bar is going to be equal to 3/8, and that's very easy to just check, but again, I'm lazy, I throw it in my calculator, times by A. So this is our x bar. And I'm going to highlight this real quick. I'm going to do this in a different color because, again, in the final, this might be the final answer. But for now, we're trying to find x bar and y bar. So just finding x bar right now, well, that's not really good enough. We found one of the coordinates, but we need two of the coordinates. So I'm going to kind of just take a break here and talk to you guys about the final. So as you guys saw, that was a lot of work to find one coordinate. We had to take two integrals. We had to evaluate them, everything like that. So if they're going to make it parametric like this, where it's h's and a's and stuff like that, I only imagine they're going to ask for x bar or y bar, but just one of the two. Asking for both of them would take a lot of time on the final. Like, look at all this work just to find one coordinate point. So if this was a final, I really highly doubt they're going to make you find both coordinates if it's all this parametric stuff. However, if these integrals were just numbers, well, then you just throw it in your calculator, you get the numbers. It's actually very, very easy. So then they might make you find both. One thing that they will never do, however, and I mean never do, and at least we're pretty deep into the video now, so hopefully none of the professors are watching, but I don't think they'll ever ask you to find the two integrals using a horizontal and vertical slice. So remember, right now I'm just using a horizontal slice, and I found one of the answers. Next, I'm going to find the other answer, and then I'm done. They'll never ask us to prove it with the horizontal slice and a vertical slice. So this video is going to be extra long, but again, you will never have to do it both ways, just one way. So right now, we found x bar. And we can come down and say, okay, we found x bar, great, but now we need y bar, so the y coordinate of the centroid. So remember how I said that the formula for y bar and x bar, they don't vary very much. So what happens is we're going to still have the integral, but instead of x squiggle, we're going to go y squiggle times dA. So the only thing that changes in this formula is we're going from an x squiggle to a y squiggle. But one thing that's really nice before we start figuring that stuff out is we can say, okay, we already know, and I'm going to change this back because I'm going to keep that green specifically for answers, is this integral right here, we already know. So what I'm going to do is just on the side here, I'm going to put the integral at dA is equal to, and we can just scroll up here, and we did it right here, this number 2 is equal to 2/3 A times H. And this is why I said when you guys are doing this in your calculator, do it as two separate calculations, because the bottom integral we're going to need to use again. So it's kind of nice to have it handy. And we also know that dA, just dA in general, because we're going to need this for the top integral, well, we already know what dA is equal to. If we come up here, we know our dA is equal to x times dy, or a to the h to the 1/2, y to the 1/2. So we got a divided by h to the 1/2 times y to the 1/2 dy. So even for our top integral, we already know one of the unknowns. The only thing now, and I'll do this in red so everyone can see exactly what I mean, is our y squiggle. That's the only thing now that we don't know. So once we find x bar, a lot of the other stuff we need to find y bar is actually kind of already known. So we're going to go up here and we're going to check, and x squiggle, well, the definition for y squiggle, so I'm going to put it in here, y squiggle, comma, x squiggle, is the distance from the axes to the centroid of the slice. So we look at this example right now, and I'm going to erase some of the old stuff. So we already found x squiggle, we don't need this. I'm going to erase these kind of bounds because we already talked about those. erase the integration area, stuff like this. So we found our x squiggle is the distance to the centroid, and we can do the exact same thing as our y squiggle is going to be the distance from the axis to the centroid. Well, that's just going to be kind of the height to the slice, and as we see here, the height of the slice right now, well, that's just going to be some parameter y, because we don't really know where the slice is located. The slice can be located anywhere in those boundaries, so it's just going to be equal to y. So if we come way down here, we know that y squiggle, well, it was mysterious, but now we know y squiggle is just equal to y. And for a horizontal slice, this is always the case. Always the case. Very, very nice. Our y squiggle is going to be equal to y every time if we take a horizontal slice. And if we take a vertical slice, so if we wanted to take a vertical slice like here, our x squiggle is going to be equal to x every single time. So that's kind of like one of those tricks. So I'm going to come up here, and I'm actually just going to write this down as every time for a horizontal slice. So y squiggle is equal to y every time for a horizontal slice. And this makes our lives a lot easier, because remember last time, if we come up to this integral, this was our x squiggle right here. This was x squiggle, and we had to make it very, very messy. I'll just put x squiggle. We had to make it very, very messy to get it in terms of y. But now we see that our y squiggle is actually already in terms of y. So what I'm going to do is I'm going to say, I'm going to come down here, because we don't need to evaluate the bottom integral, we just need the top one. So I'm going to put this as 3, and this is equal to the integral of y squiggle times dA. But now we already know that y squiggle is equal to y, so y times, and then our dA is equal to a to the h to the 1/2 times y to the 1/2 dy. And since we're still doing dy, remember, we're still taking a horizontal slice, our bounds are still going to be from 0 to h. And that's kind of another trick. If you guys are doing a horizontal slice, and this will always be the case, if you guys are doing a horizontal slice, it'll always be along the y-axis is what you're taking it as. So we're still going from 0 to h. We got our x bar, so I'm just going to highlight these right here. This y, this is our y squiggle. And then the second part right here, this is our dA. So dA didn't change from before. The only thing that changed is our y squiggle. And it's a lot easier now than it was for the x squiggle. And we can come down here and say, okay, same as before, we can take a lot of the constants out of the equation, which is perfect. So the constants that we have now are going to be a and h to the 1/2. So these didn't change from before. Then we're going to have the integral from 0 to h. And then we got y times y to the 1/2. So again, if we're multiplying integrals, we just add the two exponents. Not multiplying integrals, multiplying parameters, I guess, unknowns, parameters. We just add the exponents. So we're going to have y to the 1 plus y to the 1/2. So it's going to be y to the 3/2 times dy. And this is now our integral. So as you guys can see, it's not bad. It's just y to the 3/2. So when we come up here, the constants are going to stay the same. So we're going to have a divided by h to the 1/2 times the integral from 0 to h. Oops, actually I'm evaluating the integral now. I don't have to simplify it anymore. So same thing as before, we're going to have y, and currently it's at 1.5, and we're going to add 1, so this is going to turn into 2.5, which is the same as 5/2, and we're dividing that by the new exponent. So we're going to divide all this by 5/2. And our bounds, again, are still from 0 to h, and if we sub 0 into there, it's just going to be 0. So what we get in the end is a to the h to the 1/2 multiplied by h to the 5/2 divided by 5/2. Okay, well now we can just start simplifying things, canceling stuff like this. So remember, if we make this even easier, well, there's no other A, so this is just going to be A. And then for the H's, what we have is 5 over 2 divided by the 1/2. So we're going to minus those. So it's going to be 5 over 2 minus 1/2, which is just going to be equal to 2. And then finally at the end, we have that constant at the bottom, so I'm going to flip it around, times 2 over 5. So from here, we can say that 3 is equal to 2/5 A times H squared. Highlight these again, and I think we're using green. So this is what 3 is equal to. Ta-da! So when we're finding our y bar, we know that y bar is going to be equal to 3, our new integral, divided by 2. So we already solved for 2 before. We don't need to solve for it again. So we come over here. This is going to be equal to 2/5 times AH squared divided by what we had for 2. So we scroll all the way up here. Excuse me. Oh, I used the wrong highlighting color. These are for the final answers. I want the regular one right now. Oops. So we're dividing by this. So we know that 2, I'm going to go back up here. 2 is equal to 2/3 A times H. I have 2/3 A times H. Divide both of those together. So now we can start canceling stuff like this. So I'm going to pull out the red marker. Well, we got A at the top, A at the bottom. Those will cancel. We got H squared at the top, H at the bottom. So the square is going to cancel with the H. And then we just have to find out what those two constant numbers are equal to. And in the end, what you guys will find out is that y bar is going to be equal to 3 over 5 times H. And this is our answer. Well, this isn't our final answer, so I'm going to highlight this. So this is one of the two answers. Make this look kind of nice. So in the end, we can conclude that for our centroid, what you should do for your answer is you're going to go x bar, comma y bar. So the coordinate points of our centroid are going to be equal to, we put in brackets. So first we need x bar, which we found is 3 over 8 times A. And then comma, and then our y bar, which is 3 over 5 times H. So this right here now is our final answer, so we can box it and say this is our final answer. Perfect. So that's how you find a centroid for a continuous body. And as you guys can see, it sucks. A lot of math, a lot of everything, a lot of integration. So hopefully, and I say hopefully because I don't know what they're planning. You guys did so good on the midterm that I have no idea what they're going to want to do. I guess we'll come back to this figure. Hopefully they just give you numbers. Because if it's numbers, once you guys get the integral, so once you get to this step right here, which I'm going to highlight with the red arrow, you guys just throw in your calculator, no integration, good to go. And it's the same for the y bar. You just have to find the integrals, which we can do. So again, we're highlighting in red. Once you get to this step, you just use your calculator, you're good to go. However, if they're really mean and want a bunch of parameters, this is how you do it. And that's one of those things that if I can do it, you guys can definitely do it. My integration absolutely sucks. I'm not good at it, but it's very simple integration for this course. For this course, we're not going to give you absolutely crazy integration. That's just mean, to be honest. We're not that mean. Well, I'm not, at least. If they do give it to you, no, it wasn't me, it was them. So that's how we did it with a horizontal slice. But now we're going to get something even more fun. And we're going to say, okay, let's just say that you guys don't want a horizontal slice. You guys want a vertical slice. Do you get the same answer? Well, yes, you do. You get the exact same answer. But when you define this dA and x bar, so I'll highlight it right now in blue. So when we're coming down here and we're trying to find these, well, these will be different if we take a vertical slice. You'll get the same answer in the end, you guys will see, but your integrals will be extremely different. But you guys will end up with the same answer. It's actually very, very interesting, but it kind of sucks at the same time. So what I'm going to do is I'm going to copy this. and I'm going to bring it down, and we're going to go and do the vertical slice. So I'm going to come down here, and I'm going to say, okay, the second method, the vertical slice, and again, remember, our whole goal here is just to find one answer. We're not trying to, and so please, 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 please don't do both of these. Unless they specifically ask for a vertical and horizontal, which I've never seen them do. I don't think that they'll do, so please don't worry about it. Don't do this twice. This will just take up all your time. It'd be absolutely terrible. I don't know why this is sticking down. Oh, it's because I'm at the end of the page. Ah, I see. All right, this will work out just fine. So I'm going to erase all the crap here, because this is horizontal slice, but we're not dealing with horizontal slice. Oh, did it save as a picture? All right, I'm just going to delete this and go back up to the top, and we're going to start fresh. So I'm going to come down here, all right, up here, copy, come to the bottom, and I'm going to paste. All right, and now we can play around with this to find out what our stuff is. Excuse me. So I'm going to erase this because we're done with horizontal slice. Get rid of these slices. So now we're going to do a vertical slice. So just like the horizontal slice, a vertical slice can be absolutely anywhere on the curve. So I'm just going to put one right here. Remember, the whole point of our vertical slice is to figure out what dA, y squiggle, and x squiggle are. So this is my vertical slice. The same rules apply. dA is going to be equal to the area of the slice. So I'm going to come down here. So dA, that's still going to be the area of the slice. So now we have to come up here and say, okay, what is the area? Well, the first one that's easy is, remember, the thinnest part, oops, that's not what I wanted to do. There we go. The thinnest part here, this will always just be d times whatever we're doing. So now we're going along the x-axis. This is going to be dx. So now the hard part comes, okay, we need the height of this slice right here. The height of this slice. Well, this becomes a problem because the height doesn't exactly go to the axis. And this is why I said if you have a curve like this, you should always do a horizontal slice. This is going to become a real pain in the butt. Because remember, before we'd measure along the axis and we found out that that horizontal distance was just the formula. But now, if we're looking at this slice, and I wanted this value right here, so this value from here to here, this is going to be equal to y is equal to h over a squared times x squared. So if I know x right here, if I know this distance x, I can find that distance at the bottom. But I don't want that distance at the bottom. I want the distance I just highlighted. So this is where it becomes real messy because now this distance is going to be h, so all the way up, minus y. And this right here is why you want to try to avoid the integration on this, because now it's not just one number. Like if we look up before, we're always integrating, for example, here, we're integrating just y to the 5 over 2, or y to the 2/3, right? I'll just highlight it right here. It's just a single y. But now, once you introduce this h minus y, all sorts of problems are going to happen because you're going to have to integrate two things. So it doesn't create a lot of problems, but it's just, it gets a little messier. So this is what's going to be a problem. So when we're looking at dA, it's going to be base times height. So we know that the height is going to be h minus y. And then our base now is times dx. So this is kind of another thing you're going to have to worry about. If you choose a vertical slice, you now got dx. So what that means is everything in our formula now has to be in relation to x. So we come over here, we go, okay, so dA, I guess I'll put dA again, that won't hurt, is equal to h minus, and instead of y, we have to go to x. But what's kind of nice in this case is we already have our nice formula relating y to x. So come down here, we go, okay, y is equal to h squared over h over a squared times x squared. And then this is going to be, oops, I was about to put dA again, but this is dx now. So now it's a little bit nicer because we already have everything there. It's all in terms of x. We have no y's. But again, we have that minus sign, and that minus sign, it just creates extra integration. You want to try to avoid that as much as possible. And what we should do is just simplify this a little bit. So remember, we can remove the constants. So we're just going to say h, and we're going to go 1 minus x squared over a squared times dx. So I'm just taking that h out because it appears in both of those terms. So that's my dA. But now we got to say, okay, well, we're going to need x squiggle for the x bar, and we're going to need y squiggle for the y bar. And again, it's the same thing. It's going to be equal to the centroid. So we come to the centroid right at the center here. X squiggle is going to be really, really easy. As I told you guys, if we're taking a vertical slice, x squiggle is just going to be equal to x in all the cases. So this is x squiggle, and we know that that's just going to be equal to x. Just like how y squiggle was equal to y for a horizontal slice. So x squiggle, well, that's just going to be equal to x. So no problem at all there. But now we got a problem. Y squiggle. So remember, this has to be the distance from the axes to the point. So this distance right here, and I'm going to kind of erase the bottom here because we don't need that. We have our formula already. So this right here is going to be our y squiggle. And you guys can see how messy this gets already because we have such weird distances. So what y squiggle is going to be, it's going to be equal to, well, we need to go from the axis to the curve. So the axis to the curve is going to be equal to y. So that's this distance right here, y. And then we have to add half of the distance of that rectangle. So plus, then we're going to have h minus y divided by 2. So again, I'm going to highlight things because I know this will start confusing people. We have the y to go this distance right here. And then we have, and I'll do this in lighter blue, this term to get this distance right here. Actually, that's kind of a bad color. Let me go back because it's going into the curve. So we have this term right here to get this distance right there. So that's how we find our y squiggle. And if you look at that y squiggle, that absolutely sucks. So this is why you want to try and avoid it as much as possible. So I'm going to come down here. Y squiggle is going to be equal to y plus, I'm just going to take the 1/2 out, h minus y. So now we got x squiggle, we got y squiggle, and if I'm looking at this, I'm saying, okay, let's do x first because y looks like a nightmare. I don't want to even, I don't even want to come close to the y squiggle right now. I'll deal with that later. So remember, for the x centroid, the formula is going to stay the same. X bar is going to be equal to the integral of x squiggle times dA divided by the integral of dA. And since we now are doing a different slice with different boundaries, the integral of our dA is going to be different. It's going to have the same answer, but the integral itself is going to be different. So instead of just saying, I know it's 2/3 of a times h, I'm actually going to come in here and try and figure it out to show you guys exactly how to do this if you guys are doing different bounds. So like before, I'm just going to say this is equal to 1 integral divided by the second integral. I'm going to come down here and let's just start with dA. Why not? So 2 is equal to the integral of dA, which is going to be the integral. Now we figured out dA, so it's going to be h times 1 minus x squared over a squared times dx. And another thing I should add right here too is the way I integrate things doesn't have to be the way you guys integrate things. If you guys know little tricks, like right here, there's actually a very significant trick that you guys will learn later. But if you guys don't want to do that, you guys want to have your own way, perfectly fine. Whatever way you guys are comfortable with, I'm just showing you guys my way. I'm not great at integrating, so I try to find the simplest way. So the h is a constant, so let's take out the h, and we're going to have the integral of 1 minus x squared over a squared. And again, this is all with respect to dx. So the next thing that we're missing, of course, is our boundaries. So if we look at the dx, or I guess the with respect to thing, the d something, this is x. So what this means, integrate with respect to the x-axis. So if we come up to our curve, we know we're going from 0 and we're ending up at a. So our boundaries here must be from 0 to a. And that's because, like I said, the trick is just look at what you're integrating with respect to. In this case, we're going x. We should look at the x-axis. So from here, we can actually start our integral, because even though it doesn't look like it, it's simplified as much as you're going to really get it, unless you multiply by a squared. And so, like, you can do all the different tricks, but I'm just going to integrate this. So we know this is going to be equal to h, and then brackets, well, 1. That's really 1 times x to the 0. So this is going to turn into x. Sorry, excuse me. And the exponent on x is 1, so we're going to divide by 1, but why would we throw that in there? It's just dividing by 1. We're going to minus, and we're going to have x. So the old exponent was 2. Remember, we're going to add that up by 1, so this is going to turn into 3. And we're going to divide by the new exponents. We're going to divide by 3. But we also have an a squared at the bottom that we can't forget about. So we're going to have this. And then our integration limits are from 0 to a. So we're going to sub in 0 and a. And we see that everything inside that integral is just x's. So if we plug in 0, we're just going to get 0. So we're only going to have to worry about subbing in a. So all this is equal to h. And then in brackets, we're going to have a minus a cubed divided by 3a squared. So we can simplify this a little bit more. We see, and I'm going to take the red pen, the cubed will cancel with the a squared, so we just got a over 3. So if we were to do this, we can simplify it even more. This is going to be equal to h times a, because we can take the a out, and we're going to have 1 minus 1/3. So we simplify that even more. What we find out, and this shouldn't be that surprising, 2 is equal to 2/3 of a times h. So I'm going to highlight this because we're going to have to use it later. But what's funny is if we look up to where we took our horizontal slice instead of a vertical slice, we found that 2 is equal to 2/3 ah. We come down here, 2 is equal to 2/3 a times h. Starting to lose my voice a little bit. This is going to be a little bit of a longer video, but I'm sure that won't bother you guys at all. So, excuse me. As I said, no matter what method you guys do for the slices, you guys are going to get the exact same answer. So it doesn't matter too much. So coming down here, we found 2, but remember, we also need the top integral. So we can go 1. It's going to be equal to the integral. It's going to be the integral of x squiggle dA. So we know this is going to be the integral, and the bounds are going to stay the same, so it's going to be from 0 to a. X squiggle, well, what's nice is that's just equal to x, and then times dA. Well, dA is the one that kind of blows, so this is going to be times h, 1 minus x squared over a squared, and all this is with respect to x. So I'm going to remove some of the constants, and then I'm also going to multiply the x in. So the constant here is h, so equal to h. The integral can be from 0 to a, and then I'm going to multiply the x into everything. So this is going to be x minus x cubed divided by a squared. And this is going to be with respect to x yet again. So again, not that hard. It's just a little bit more messy because we have the minus sign. We want to try to avoid that because that's just no fun. Come down here. We can integrate it, so the h is going to stay out. Excuse me. So x to the 1, we're going to bump up the power and divide it by the new power. So this is going to go to x squared divided by 2. Same thing for this one. We're at x cubed, so this is going to change to x to the 4. We're going to have to divide by that new power. So we're going to have divided by 4, but then we also have an a squared. We can end this. This will be from 0 to a. So you come down here, we can just start simplifying. We're going to have h, and we got a squared divided by 2. minus a to the 4 divided by 4a squared. So when we do this, we can go back to the red marker, start crossing stuff out. A to the 4 and a squared are going to cancel, and we're going to be left with a squared on top. So now we got a squared minus a squared. We can factor out the a squared. And this is equal to a squared times h. And then in brackets, we're going to have 1/2 minus 1/4. So when we come down even further, what we find, excuse me, is this is all going to be equal to 1/4 a squared times h. And this is equal to 1. So I'm going to highlight this because we'll probably use this later. And if we look up way to the top, we see that 1 is equal to a squared h divided by 4. So it's the exact same answers, just different procedures. So it won't surprise you that when we go x bar is equal to 1/2, or 1 divided by 2, we're going to get 1/4 a squared h divided by 2/3 ah. Oops. The quality of this video is drastically decreasing. Alright, go like that. And there should be an h at the end here. So what we do is we're going to find out that x bar, unsurprisingly, is equal to 3/8 times a. So I'm going to highlight this in the green color because this is one of the coordinates. And if we scroll up to the top for our x bar up top, we see that x bar is 3/8 times a. Come down here, 3/8 times a. So one of them's already done, same as before, no big deal. But now we got to go to the one that we've been kind of dreading, and that is the stupid y bar, because as you guys saw, y squiggle is just a mess in this case. But we have to do it. I like helping you guys, although I'm regretting it now. So we got the integral of y squiggle times dA divided by the integral of dA. So dA we already know, or the integral of dA we already know, because we already solved for it for our x squiggle. So the integral of dA is equal to 2/3 a times h. So now we just have to find out, and we'll just go, this is equal to 3/2. Excuse me. So all we have to do is find out what 3 is equal to. 3 equal to the integral from 0 to a. Y squiggle, well, we're going to have to throw that in there. Come up here. We see that y squiggle is equal to y plus 1/2 h minus y. But again, we can't integrate with respect to y. We're integrating with respect to x. So we're going to have to modify all the y's into h/a squared times x squared. So this is going to be h/a squared x squared plus, and then brackets, h minus h/a squared times x squared. And this right here, that right there just by itself, oh, and then we got the 1/2 too, can't forget about that. That right there is just our y squiggle, and this is why that one sucks so badly. And to make matters worse, that's just y squiggle. We need to find dA too. So we come up here, we know that our dA is equal to h1 minus x squared over a squared times dx. So come down here all the way to the bottom. We have, oh, I guess I shouldn't have put the bracket, sorry. We got h minus, oops, I'm messing this up because it's getting too long. H minus 1 minus x squared divided by a squared and this is times dx. So that's our integral. However, that's a mess. That's an absolute mess. And what happens is it actually simplifies very, very nicely. But you guys will never see that if you guys do it this way. So what I recommend for this kind of purpose, if you ever have an integral and its y squiggle is just so gross, what I recommend is just keeping it in terms of y until we simplify it as much as possible. So this right here, I'm just going to put gross. So we know that there's going to be some relationships, but it's hard to point out when the integral is that long. So instead, let's just go up here and let's keep everything in terms of y until the very end. So this is equal to the integral from 0 to a. What's y squiggle equal to? So we come up here, we see y squiggle is equal to y plus 1/2 h minus y. So I come down here. So we can simplify that into 1/2. Oops, I guess I'll put the 1/2 first. 1/2, and 1/2 of y plus, y plus 1/2 of h minus y is equal to just the 1/2 of y plus h. And then dA is equal to y plus h dx. So this is how things start to become a little bit nicer, but it's not the best. It's still kind of sucks. But it is what it is right now. And I just need to check something. Perfect. So it's all good. So not the best, but we can go through. This is equal to the, and we can take the 1/2 out. The integral from 0 to a. And we got, so now we're just going to multiply everything. So y times y is y squared. Y times h is y plus h, so plus yh. H plus y, oops, there's a mistake somewhere. This is h minus y, this is the problem. I got too far ahead. H minus y, oops. So it's going to be the same thing, except we're going to have minus yh and then plus h squared dx. So we can cancel those two, so it's going to be equal to the integral of 1/2 the integral from 0 to a of y squared plus h squared. Or sorry, h squared minus y squared. Yeah. Sorry guys, I just lost my brain for a second. So we do this, this is actually a negative y squared because of the mistake at the top. So it's h squared minus y squared. The moral of the story here for you guys is don't do a vertical slice when you got something like this. It just turns into a mess. So this integral is much more manageable, but it's still y, and we're integrating with respect to x. So now we can come down and do our substitution. So this is equal to 1/2 the integral from 0 to a of h squared minus, and then we're going to substitute our x. So we're going to have h over a squared x squared, and then all this is squared times dx. So now we have everything in terms of x. Excuse me. We can simplify this further, so we're going to have equal to h squared divided by 2. So each term is going to have an h squared times the integral from 0 to a of 1 minus x to the 4 divided by a to the 4 times dx. So still really, really bad. Not as bad as before, but we're going to have to integrate x to the 4. And a lot of you guys start to get scared once the exponents get high, but it's the same rules that always apply. So this is equal to h squared over 2. So the constant stays the same. And then in brackets, 1, the integral of 1, well, that's just going to be equal to x. And then minus, we got x to the 4, so that's going to bump up to x to the 5. Divided by, so remember, we're going to have to divide by that 5, a to the 4. And this is from 0 to a. So we can substitute a in to get h squared divided by 2. Then in brackets, we're going to have a minus a to the 5 divided by 5a to the 4. So it's funny how it always looks complex, but a lot of things will cancel out. Oops, wrong one. So this 5 will cancel out with the a to the 4. So in the end, what we have is AH squared divided by 2. And in brackets, we're having 1 minus 1/5. So you guys substitute that all in the end, what you guys will get, and I'll put this down here, is 3. So the integral, whole thing is going to be equal to 2/5 times AH squared. Highlight this, and boy, I'm sick of integration now. And what kind of scares me is for moment of inertia, the integration only gets worse because there's extra terms. But it's kind of funny because for moment of inertia, what you guys will find is you cannot pick a vertical or horizontal slice. You have to pick a very specific slice, and I'll show you guys exactly what you guys, or how to pick the slice for that one. So it actually gets a lot nicer because it's kind of foolproof and you don't have to pick the harder method like I did here to show you guys. But if we divide, so we got y bar is equal to 3 over 2. So this one is going to be equal to 2/5 a times h squared over 2/3 a times h. Divide them. What you guys will find is that y bar is going to be equal to 3 over 5 times h. So I'm going to highlight this with the green, because again, this is just one of the coordinates. It's not our final answer. Our final answer wants both of the coordinates. So we can say at the bottom here for our centroid, x bar comma y bar is going to be equal to, so we scroll up, x bar is 3/8 of a. So we got brackets 3 over 8 times a, and for y bar we got 3 over 5 times h. So I'm going to put a red box around this like that, and that is it. So if we come up to our other answer, it's exactly the same. So it doesn't matter which way you do it, the final answer is going to be the same. The adventure to get that final answer, that's when things are going to start changing and get gross and stuff like that. So for this one, like I said, you want to always pick a slice that you can go directly from the axis to the end of the curve. So if I'm going to highlight these right now in blue, if I look at this horizontal slice, it goes from the axis right to the curve. There's no jumps in between. If I look at the vertical slice, I have that jump in between the curve and the axis. So that's why things get really, really messy. So you want that nice slice, basically. So that was a lot, but it concludes centroids for continuous bodies. Next time we're going to talk about centroids for composite shapes, and those are a lot easier, trust me. This is going to be the hardest part if you hate integration. The next part is really, really simple. So thank you guys all so much for listening and sticking in there. I know this is going to be quite a long video, but so again, thank you guys so much. I hope this helped, and I'll see you guys in the next video.